Thermochemistry is the study of energy changes that occur during chemical reactions and during changes in state. In this short video about thermochemistry, we will discuss how energy is conserved in a chemical or physical process, and how we can determine the amount of energy absorbed or released in a chemical or physical process. Energy is the capacity for doing work or supplying heat. In thermochemistry, the energy change of a system is calculated by adding the work done on the system and the heat transferred to the system. The work, symbol W, done on a gas or by a gas is found by multiplying the pressure times the change in the volume of the gas. In this chapter we will focus on the heat, which is represented by the symbol Q. The system is part of the universe on which you focus attention. The surroundings is everything in the universe, outside the system. In a chemical reaction, reactants are the system, and everything else is the surroundings. Remember that heat flows from high temperature to low temperature. The law of conservation of energy states that, in any chemical or physical process, energy is neither created nor destroyed. In a chemical reaction, the reactants are the system, and everything else is the surroundings. Chemical potential energy is the energy stored in the chemical bonds of a substance. Bond breaking always requires energy, and bond forming always releases energy. As can be seen from this figure, when the atoms are separated, they have a higher chemical potential energy than when they are bonded. During a chemical reaction, one substance transforms into another substance. The new substance has a different amount of chemical potential energy. Heat is energy that transfers from one object to another, because of a temperature difference between the objects. A process is called endothermic, when heat is absorbed from the surroundings, so the value of heat is positive. A process is called exothermic, when heat is released into the surroundings, so the value of heat is negative. Because energy in the universe must be conserved, the heat absorbed by the surroundings is equal to, but has the opposite sign of, the heat released by the system. To illustrate the direction of heat flow, let's look at a couple of examples that most of us are familiar with. 1. During the melting of ice, heat is absorbed from the surroundings, so that is an endothermic process. 2. Burning wood or gas releases heat to the surroundings, so that is an exothermic process. Heat flow is measured in two common units, the calorie and the joule. 1 calorie is the quantity of heat required to raise the temperature of 1 gram of pure water by 1 degree Celsius. Note, 1 dietary calorie is equal to 1 kilocalorie or 1000 calories. Use capital C when referring to dietary calories. Don't forget that the unit of calorie used for measuring heat flow is not the same as the calories shown on food labels. A cheeseburger from McDonald's is about 300 dietary calories, or 300,000 calories. 1 calorie is equal to 4.184 joule. The amount of heat needed to increase the temperature of an object by 1 degree Celsius is the heat capacity of the object. The heat capacity of an object depends on its mass and its composition. The greater the mass of an object, the greater its heat capacity. And different substances with the same mass have different heat capacities. This leads to the concept of specific heat, for which capital C is used as the symbol. The specific heat is the amount of heat needed to increase the temperature of 1 gram of a substance by 1 degree Celsius, and can be calculated by the formula that is shown here. Q is the heat in joules or calories. M is the mass in grams. Delta T is the change in temperature in degrees Celsius. The specific heats of some common substances are shown in this table. It can be noticed that water has a high specific heat compared to the other substances. Enthalpy is the measurement of energy in a system. The quantity of enthalpy equals to the total content of heat of a system, equivalent to the system's internal energy, E, plus the product of volume and pressure. The heat absorbed or released by a reaction at constant pressure is equal to the change in enthalpy, symbolized as delta H. The background information is shown for information only. For now, we only need to know that the enthalpy change is the amount of heat that is absorbed or released during a process that occurs at a constant pressure. Let's discuss how we can measure and express the change in enthalpy. As the name suggests, a calorimeter measures the calories. Calorimetry is the measurement of heat flow into or out of a system, during a chemical or physical process. Remember that at constant pressure, the heat flow is equal to the enthalpy change. Foam cups can be used as a simple calorimeter. To carry out a constant pressure calorimeter experiment, do the following steps. Dissolve the reactants, which is the system, in known volumes of water, which is the surroundings. Measure or calculate the total mass of the water solution. Measure the initial temperatures of each solution and mix. Measure final temperature after completion of the reaction. If the values of the mass, specific heat of water and the change in temperature are known, the enthalpy change for the reaction can be calculated. Here is an example that illustrates how to measure the enthalpy change in a calorimetry experiment. When 25.0 milliliters of water containing 0.025 moles hydrogen chloride at 25 degrees Celsius is mixed with 25.0 milliliters of water containing 0.025 moles of sodium hydroxide at 25 degrees Celsius in a calorimeter, the temperature increases to 32 degrees Celsius. Assume the densities of the solutions are 1 gram per milliliter, and the final volume is 50 milliliters. In this example, water is considered as the surroundings. First step. Calculate the total mass, using the volume and density. Second step. Look up the heat capacity for water, which is equal to 4.18 joule per gram, per degree Celsius. Third step. Calculate the change in temperature. Final step. Calculate the enthalpy change. Thermochemical equations are chemical equations that include the change in enthalpy. The heat of reaction is defined as the enthalpy change for a chemical reaction. In an exothermic process, the system releases heat to the surroundings. In the thermochemical equation for an exothermic process, the energy released is considered as a product. Since the chemical potential of the reactants is larger than the chemical potential of the products, the enthalpy change is negative, as shown in this figure. In an endothermic process, the system absorbs heat from the surroundings. In the thermochemical equation for an endothermic process, the energy absorbed is considered as a reactant. Since the chemical potential of the products is larger than the chemical potential of the reactants, the enthalpy change is positive, as shown in this figure. The heat of combustion is the heat of reaction for the complete burning of 1 mole of a substance. Think about the combustion of methane, which is an exothermic reaction, releases 890 kJ of heat. The heat of combustion is minus 890 kJ. Heats of combustion are measured in a constant volume bomb calorimeter. A schematic diagram of a bomb calorimeter is shown. The molar heat of fusion or melting is defined as the heat absorbed when 1 mole of a solid substance melts to a liquid at constant temperature. It's important to note that the gain of heat causes a change of state, instead of a change in temperature. Fusion, which is an endothermic process, of 1 mole of ice at 0 degrees Celsius to 1 mole of liquid water at 0 degrees Celsius, requires the absorption of 6.01 kJ of heat. The molar heat of solidification is defined as the heat released when 1 mole of a liquid substance solidifies at constant temperature. Solidification, which is an exothermic process, of 1 mole of liquid water at 0 degrees Celsius to 1 mole of ice at 0 degrees Celsius, requires the release of 6.01 kJ of heat. The molar heat of vaporization is defined as the heat absorbed when 1 mole of a liquid substance vaporizes at constant temperature. Vaporization, which is an endothermic process, of 1 mole of liquid water at 100 degrees Celsius to 1 mole of vapor at 100 degrees Celsius, requires the absorption of 40.7 kJ of heat. The molar heat of condensation is defined as the heat released when 1 mole of a vapor condenses at constant temperature, which is the normal boiling point. Condensation, which is an exothermic process, of 1 mole of water vapor at 100 degrees Celsius to 1 mole of liquid water at 100 degrees Celsius, requires the release of 40.7 kJ of heat. Fusion and solidification are reverse processes that occur at a substance's melting point. Vaporization and condensation are also reverse processes that occur at the boiling point. The table lists the molar heats of fusion and molar heats of vaporization for several substances. Look up the heats of physical change for water. You will notice that the molar heat of vaporization is significantly higher than the molar heat of fusion. This figure shows the relationships between the heats of vaporization, condensation, solidification, and fusion. Endothermic processes that absorb energy from the surroundings are represented by the arrows that point up. Exothermic processes that release energy to the surroundings are represented by the arrows that point down. A heating curve shows the enthalpy changes that take place during phase changes. You can see the enthalpy changes that occur as water changes from ice to liquid, and then to vapor. Where the curve is flat, heat added does not cause a rise in temperature. Rather, the heat gained or lost is used to change the state of water. Hot or cold packs are applications of heat of solutions. These packs cause the temperature to change due to formation of a solution. In a hot pack, calcium chloride mixes with water and releases heat. Cold packs contain solid ammonium nitrate crystals and water. Once the solute dissolves in the solvent, the solution becomes cold. When 1 mole of sodium hydroxide is dissolved in water, the solution can become so hot that it steams. The heat from this process is released as the sodium ions and hydroxide ions interact with the water. The temperature of the solution increases, releasing 44.5 kilojoules of heat as the molar heat of solution. It's possible to determine a heat of reaction indirectly using Hess's law of heat summation. Hess's law states that, when adding two or more thermochemical equations to give a final equation, you add the heats of reaction to give the final heat of reaction. Example: calculate the enthalpy change for the conversion of diamond to graphite. The enthalpy change for this reaction cannot be measured directly. We are going to use Hess' law by using the following two equations. The formation of carbon dioxide from graphite and oxygen. The formation of carbon dioxide from diamond and oxygen. Now, we have to write equation 1 in reverse. Note: when you write a reverse reaction, you must also change the sign of the enthalpy change. Add equations 2 and 3, and you get the equation for the conversion of diamond to graphite. This figure shows how Hess's law of summation works. In this example, Hess's law is used to determine the enthalpy change for the conversion of diamond to graphite. The heat of reaction can be calculated as well, using the standard heats of formation. Standard heat of formation is defined as the enthalpy change for formation of 1 mole of a compound from its elements, with all substances in their standard states. Standard states of conditions refer to the stable form of a substance at 25 degrees Celsius and a pressure of 101.3 kilopascals. A pure element in its standard state has a standard enthalpy of formation equal to 0. Note that the elements hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine occur naturally as diatomic molecules. The equation shown can be used to calculate the heat of reaction, using the standard heats of formation of the products and reactants. This table shows standard heats of formation for several common substances. The standard heats of formation for other substances can be found in reference materials or through online search. As can be noticed, the standard heat of formation for a free element in its standard state is equal to 0. Example: bromine in its standard state is a liquid, and is a diatomic molecule. Let's do an exercise and calculate the heat of reaction for the following chemical reaction. When solid aluminum powder reacts with iron 3 oxide, it produces aluminum oxide and iron, in a highly exothermic reaction. Look up the standard heats of formation in the table shown previously. This reaction is known as the thermite reaction and is highly exothermic.
Here is a mixture of aluminum and iron oxide.
All
this
right.
is a thermite mixture.
Again, another thing that you just might not have laying around the house.
You probably would not have that laying around the home.
We do have flower pots though. Okay.
We do. And we're going to put the thermite in the flower pot.
All right, but it has a hole in the bottom.
That's why we have the cardboard.
Alrighty.
Put a little piece of cardboard on top. We're going to pour the mixture in, put it in another clay pot just for safety. Mm-hmm. Okay, and then what we're going to do is we're going to ignite that using a jumbo sparkler.
Oh boy. Everybody watch at home. Oh wow,
So there we
all
go.
right.
Put that in there.
Oh, okay. Oh wow.
Yep.
Oh wow,
Yep.
okay.
Yep. So right there, liquid iron.
That's liquid that's
That is
dropping into
liquid
the
metal.
sand.